Some reactions of the hexa-aqua aluminium 3 ion are shown below. Give the formula of the white precipitate B. So what we've got here, we've got the hexa-aqua aluminium ion reacting with sodium carbonate. So we need to remember that when a 3+ ion reacts with carbonate, then because the 3+ ions are smaller and more highly charged than 2+ ions, they act as acids, and they donate protons to the carbonate, and we get CO2 and water, as well as the hydroxide of the 3+ ion. So the formula of the white precipitate would be that we have 3 waters still present, but 3 of the waters have been deprotonated, donated their protons to the carbonate ions, and we've got this aluminium hydroxide. And it says, state one other observation. Well, because the CO2 is being evolved, we would see effervescence or fizzing. And then we need to write an equation. So we've got the aluminium ion. I'm not going to put the sodium in for ease of not having the spectator ion. Now, if we look at these charges, there are 3 pluses and 2 minuses. So to make the charges balance, we're going to go for a common factor, common multiple of 6. So 2 aluminium ions and 3 carbonate ions. So we're going to get 2 of our precipitate. You don't actually need the square bracket because it's uncharged, but I've put it on anyway. And then we'd have 3 CO2s and 3 waters. Give the formula of the complex ion C. So when you add sodium hydroxide, a white precipitate that reacts to form a colourless solution containing complex ion C. So at first, when you add sodium hydroxide, you get the same white precipitate that you just got with the carbonate. But when you keep adding it, the colourless solution that forms, a complex ion, something with a charge, is when you remove yet one more proton. So you have 2 waters and 4 OHs and a 1- charge. That would be our formula of C. And the condition is that we have to have excess NaOH, so we keep adding it until it's in excess. And then if we were to give an equation starting from the hexa-aqua, we can see that we're going to need 4 OH minuses to remove 4 protons from 4 separate water molecules to leave us with 2 waters, 4 OHs and the minus, and we've made 4 waters by removing protons. Deduce the formula of complex ion A. So let's go back and look at that. We're adding EDTA. So the complex ion, we need to remember that EDTA, and we can see it from here, if there's 4 NAs, is a 4- ion. We also need to remember it's a hexadentate ligand, so it's going to swap all 6 waters for the EDTA. So it's going to be aluminium and then EDTA. So remembering that Al was 3+ and that EDTA is 4-, then this complex ion would have a 1- charge. Explain using an equation why a solution has a pH less than 7. So we sort of talked about this at the beginning. Aluminium, the hexa-aqua ion, is acidic because it's small and highly charged, so it is able to donate protons to water in our solution, or to alkali. You could put a formula with an alkali in there, but it says why a solution containing it, so it's good to just show it with the water. Why it has a pH less than 7. So our explanation is Al3+ is small and highly charged, has a high charge density. So is able to polarize water molecules and weaken OH bond in water, and that allows it to release H+ ions, and that's what makes it acidic.